As lesson 8.2 is another look, I will say our final look at particle motion. We have done a lot with the physics side of calculus, with position and velocity acceleration, and we're going to dive into it one more time. Okay? So, particle motion problems that deal with motion along a straight line. This includes horizontal and vertical motion of a falling object. It's important to note that the motion meant the particle was moving along an axis, not along the graph of the function, so thus along the straight line. Now, it's possible for us to work in two directions. For an example, if an object is traveling a straight line, then its velocity can be expressed as the integral of acceleration. Now we'll focus on getting a better understanding for how to model motion problems that will appear on the AP exam. Okay, net change theorem, net change theorem, the definite integral of the rate of change of a quantity f prime of x gives the total change, or net change, in the quantity on the interval. So, stating the idea that an integral can be used to define net change. When we see, keep in mind, when we see an integral written out like the definition, we usually see the integral from a to b of lowercase f of x equals capital F of b minus f of a, correct? That's what we normally see for our definition of an integral, how to use fundamental theorem of calculus. Realize where f, lowercase f is your original function, capital F is your antiderivative here. Okay, so net change is talking about the integral of the derivative and subbing in. I mean, basically, you're just changing out the capital F prime from the lowercase. Okay. We're going to do a lot of word problems, okay? A lot of thinking through that way. Three main question stems. So, in other words, as we think ahead to what are you going to see on the AP, okay? When given an object's velocity and a question stem is asking about the object's position, we need to understand which definite integral is necessary to respond to the prompt accurately. In other words, what are they wanting? Are they wanting displacement? Are they wanting total distance? Or are they wanting actual position? Okay. All three can be done with an integral, but what are they asking? Okay, and I'll say me as the AP teacher sometimes struggle. You know, I struggle to think about, okay, wait, which one are they asking? So, displacement. Okay, displacement being how far are we from our starting point, essentially, right? You guys know the physics definition, so I don't really have to define these. But your displacement is the integral from a to b of, in this, or for displacement, velocity, right? You're integrating velocity. Now, keep in mind, when you're just doing that integral, there can be positive and negative pieces, right? So, for example, if we look at this picture here, remember the area under the curve above the x-axis is going to have positive values, right? Where the pieces under the x-axis, between the curve and the x-axis, are going to have negative values. So just the idea that the displacement for a situation like this would be the area of 1 minus the area of 2, because it's below the x-axis, plus the area of 3. So that's not going to be total distance, because you're subtracting pieces in there. Okay? With total distance, that's more where we want it to be all positive, because you're adding all your distances up, and so then it's the integral of the absolute value, and you're adding a1 plus a2 plus a3. Total distance, you need to be aware of what your graph is doing, because if part of your graph is below the x-axis in the interval you're talking about, you need to be aware of that, and you need to break it into the pieces, and we'll go through that. And then actual position. So actual position, you have to take into the initial condition. Where is your starting position? It's not necessarily, you know, at 0. So where's your starting position plus the displacement? Now, to kind of connect here and show the differences, look at this exploration piece. Given that S of 0 is 4, so the initial position is 4, Find displacement, total distance traveled, and position on 0 to 10, where v of t is measured in meters per second. So if we're going to do displacement, okay, displacement, change in position from beginning to end, yes. And I'm going to put these each with their little pieces here. If I'm doing displacement from 0 to 10, the integral from 0 to 10 of v of t dt, what's the math I would have to do based on that graph? So using this graph here, what's the math we're doing? We're trying to find the integral from 0 to 10. What are we doing, 18 and 12? Subtracting them, right? Because 18's above, 12's below. So this one, displacement, is just going to be 18 minus 12, which is 6. And unit length was meters, so 6 meters. As opposed to total distance. Well, total distance, it's still your integral from 0 to 10, but we want to say the absolute value within that integral. And so this would be one that you'd be breaking up into pieces. You've got the 18, but what do we have to do with the 12? We're going to add it, right? Even though you're maybe going backwards, you're still traveling 12 whatever meters. So in this case, 18 plus 12, which is 30 meters. And then actual position. Actual position, you want to pay attention to initial condition. So this is going to be our initial condition, which our initial condition was given as 4. And so 4 plus the integral from 0 to 10. Right. Yep. So it ends up being 4 plus 6, which is 10. Okay, because actual position is going to be initial position plus displacement. Where are you in relation to where you began? Okay, so you'll have to watch. As I've been working through the homework, I found myself flipping back to the notes to double check myself, no, displacement versus total distance, what you're doing there. Okay, let's look at a velocity graph. The graph at the right represents the velocity, v of t, which I'm always checking what is physically labeling my graph. I know it sounds silly, but you don't know. Are they going to give you a velocity graph, a position graph, an acceleration graph? Like, I'm always checking that. So the graph represents the velocity of a particle that is moving along the x-axis on the interval 0 to 8. V of t is measured in inches per second. So what interval of time is the particle moving to the right? And justify your answer. So don't overlook that word there, justify. So when would a particle be moving to the right? And why 0 to 3? Okay, so a particle moves to the right when velocity is positive, yes? So is that the only place?
7.
And also 7 to 8, yes? Now, what's my justification? Justification. Yeah. Yeah, when velocity is positive, the particle moves to the right, and that happens on 0 to 3 and 7 to 8. How do we say?
Greater than 0.
Yeah, you could say just when velocity is positive, but mathematically sound would be to say v of t greater than 0. Excuse me. So when v of t is greater than 0, particle moves right on, I'm going to write it as 0 less than t less than 3. And what was the other one we said? 7 less than t less than 8. Your justification is getting in there that you know the particle moves right when the velocity is positive. That is your justification there. Obviously, put a coherent thought, coherent sentence, not just v greater than 0 and then your answer. Okay? Okay. B? I feel like it's been an eon since we've talked about this stuff. I know you guys talk about all the time in physics, but I feel like it's been a bit. On what interval or intervals is the particle slowing down? When does a particle slow down? When what? More than just that.
When it's opposite sides, right?
Right.
Because it's negative if it's above the x-axis and positive if it's below the x-axis.
Okay, so it's coming back to us. And I don't know if it's your calculus brain or your physics brain working right now, or if they're working in tandem, but okay. We've talked about this. It's been a lot. It's been a while though. I will say that. So we're looking for opposite pieces here, right? So we are looking for, you'll often hear in calculus when velocity and acceleration have different signs, okay? In this case, we have a velocity graph, yes? And so as we think about that, so on my velocity graph, from 0 to 3, my velocity is positive, yes? What are we looking for in terms of acceleration? Negative acceleration, which is going to happen where?
2, 3.
Yeah, and I'm not going to leave this on here. I'm just circling it for the moment to get our pieces. But right there, there's a situation where velocity is positive because we're above the x-axis. But acceleration is negative because acceleration is the derivative of velocity. So acceleration is a slope. Anything in the 3 to 7 time range? Okay, because from 3 to 4, we've got negative velocity and negative acceleration. But over here on 6 to 7, we've got negative velocity and positive acceleration. What about 7 to 8? That's positive, positive, isn't it? Okay. Now, so many different ways to state this, but you have to put an explanation into play, right? So I have it 2 different ways in my notes because I start off with where V of t and A of t have different signs, the particle is slowing down. So I listed when velocity is greater than 0 and acceleration is less than 0, that interval, and then I flipped it also. You can also use when the graph is decreasing and above the x-axis, or when when the graph is increasing and below the x-axis. What's better? I don't necessarily think either of them are better. I think, put into words there. So I will say, just as a reminder, I'm going to start off saying when A of t and B of t have opposite signs, the particle is slowing down. Okay, and then pick one way or the other to explain. Let's see. V of t is greater than 0, and A of t is less than 0 on 2 less than t less than 3. and v of t is, whoops, less than 0, and a of t is greater than 0 on the interval from 6 to 7. Again, far from the only way to explain. And I kind of like the whole idea of the graph is decreasing above the x-axis or increasing below the x-axis. That works well too. I'm going to get those pieces off my graph, maybe. Gosh. Okay, C. When is the particle stopped and changing directions? Again, love saying this. Justify your answer. What are we looking for here?
When v equals 0, so crosses or touches x-axis.
Okay, when velocity is 0. And so my cases of where the velocity is 0 is going to be at 3 and 7. Okay, so yeah, when velocity is 0, particle is stopped. And that happens at t and, or actually, okay, when velocity is 0, that's when particle is stopped. When are we changing directions? When velocity also changes sign, right? Because if it just touches the x-axis, are we really changing directions? No, you would still be going the same direction. Okay. I'm going to say, how do I want to say this? Particle is stopped at t equals 3 and t equals 7. Since v of t equals 0. And also changing directions because v of t changed signs. Okay, and do you know how to answer the last one? On what time interval is the acceleration 0? And of course, again, because you just love to justify your answer, when is acceleration 0? See, Ethan going over here. So what is that in words?
V of t is the same, like your state's consistent.
Okay, so one option of explanation is when the velocity is constant. Okay, and when velocity is constant, that means the acceleration is going to be 0, right? Because that's a 0 slope. So when velocity is constant, a of t equals 0, and that's happening on those two time places, or two intervals there. When v of t is constant, a of t equals 0 on, what do we have? 1 to 2 and 4 to 6. Okay. You guys have your calculators with you today, right? Okay. You can move over there and sit if you need to. Okay. The next one is a table problem. And AP likes to give you tables. Okay, you will see some tables on AP, whether it be a multiple choice, your response, both. You're going to see table problems. So, a city bus accelerates as it leaves one stop and then decelerates as it comes to another stop. The chart below measures the velocity v given in miles per hour between each stop. Okay? So notice we have a time piece of our chart. And notice that time is measured in what? Minutes. Are you noticing a disconnect here? It's kind of annoying, but we're going to have to deal with it, aren't we? That here we have miles per hour, and here we have minutes. Going to make you think, going to make you work here. And then we have a velocity, and that velocity is given in miles per hour. Okay, so probably the first thing we're really going to need to do is to fill in the chart, because A asks us to find the distance in miles the bus travels between every interval stop using the trapezoidal rule. Okay, pulling all the pieces together here. So, trapezoidal rule. What's that area of a trapezoid again? Okay, so just because we all need this reminder, trapezoid area is 1/2 times the height times V1 plus V2 is how I remember it. Different people do different pieces, but you have to remember that, right? In order to be talking about trapezoidal rule. Now, if we pick one of these, because here's the deal. I don't really care for this problem. They didn't give us room to show the work. But, I don't know, maybe that's good. Maybe you don't want to show the work. But I'm going to pick one and to do as an example. Because we don't have room to do all this work because we have to fill in what? Like 9 boxes. So, let's pick one in the middle here. I'm going to do the interval from 20 to 25, just because it's in the middle and that will make it work for us pretty well. If we're doing the example where we're going from t equals 20 to t equals 25. Okay, well, how do we do that area? We know we're going to be doing 1/2, got that, right? Height. What's the height?
5.
5 because it's the distance between the two, yes? Now, pause that. Okay. I agree the height is 5 in terms of 20 to 25 is a distance of 5. But remember we had a unit disconnect here.
Oh, wait. No.
Again, not fun, okay? We have a unit disconnect. This time is in minutes, but our velocity is in miles per hour, and we have to give a distance. When we give that distance in the end, that distance is going to be in terms of miles. So that 5 is 5 minutes, yes? Okay. What do you know about 5 minutes?
It is 0.083 hours.
Okay, it is 0.083 hours, and how did he get that?
Divided by 60.
It is 5/60ths of an hour. Is that an easier way to say it?
Probably.
Now, I get it. We'll eventually talk decimals, but so the idea is 5 minutes is 5/60ths of an hour. Agreed? And you can reduce that. You can use decimal form. You can do whatever. I'm just trying to put it up here so when you look at it later and it's not just 5, you can be like, why? So my height between the two is 5/60ths. And then it's base 1 plus base 2. What are the bases? Those are your y values, so to speak, the heights of the bar. And so that is 32 plus 4. Are you following? This is where you grab the calculator, right? The 1/2 times the 5/60 times the 36. And you get a nice, neat 1.5. Okay? Now, when we're doing this, that's the interval from 20 to 25, which means in terms of distance, from 20 to 25, your distance is going to go over here at the right. And I know I'm kind of jumping into the middle there, but now we've got to do this for like 8 other boxes. Good practice. You can find space and write them all down if you want, but you can also just use your calculator, can't you? As we look at this first, well, okay, what goes in the first box? That's 0, yes? Which is why everything's going to end up in the right-hand box of the interval. Because at time 0, your velocity is 0 and your distance traveled is 0. Okay? I'll write them here and then I'll end up erasing them, but what do we have? 1/2 times 1/2. 5/60 is the distance between the two, and then 0 plus 18. And that gave you what? 0.75. Okay? That was from 0 to 5. Next, 5 to 10. Let me know what you get. 1/2 times 5/60 times 18 plus 6 is 1. Okay. What's my next interval? Oh. You did it wrong. Look at your interval.
Oh,
Jacob's words, not mine, but it's very true. What's the catch? It's 10. Oh. So now I've got 1/2 10/60 and 6 and 32.
No, parentheses.
What do we get here?
No.
We don't get no.
3.167.
Yeah. I have it written down as 3.1667. So
Jumped all the way up to 3.
This is a whole nother.
we also doubled the length of the interval too.
Why would you do that?
So
Who does it again?
okay, 20 to 25 we've already done, haven't we? So 25 to 30. 1/2 25 to 30 is going to be, we're back to 5, right? I guess I'm going to end up writing these down here. They just, you can't really tell what they are unless you know what you're doing. So what is it, Maddie?
1.6667.
Yep. 1.6667 or 667. And I think Ethan already mentioned it. Next one. 1/2 10/60 and we at 36 plus 12, which is 4. Huh? Oh, what?
I don't like this.
So what's my next interval? 15. One half 15/60 12 plus 22, which is 4.25. And last one.
That's only 5.
Oh, we jumped back down to 5, huh? 0.916 repeating, so I put 0.9167. I've been going 4 decimal places in this section just because, so AP says 3, but if I have to shorten these numbers, and if I have to do anything else with these numbers, that's why I've been putting 4. But okay, so A was find the distance in miles the bus travels between every interval stop using the trapezoidal rule. Okay, B, find the total distance the bus travels in 60 minutes.
Multiply the distance or the time.
You're making it too difficult.
Can we just
Add the 5.
Just add them. Make it too.
Decimals.
Well, and here's the deal, guys. When I did this one on my own, I went back up and arrowed up because I had all these values in my calculator, didn't I? And I got, because of that, I'll be honest, I got a slightly different answer than what she has in her answer key.
It is.
I'm not made up in a lot of work.
Okay, well, anyways, you're adding them all up, right? You're adding the values we just found. However you go about it, what answer are you guys getting?
I got 17, so 251.
I guess
17 point what?
251.
251?
But I
I
have
got
different decimals.
2.5.
I use fractions.
Yeah, I guess.
Okay, so when I did this on my own and I went back up into my calculator and grabbed like the 0.916666 and the 1 point, like when I grabbed the big long decimals, I got exactly 17.25. If you look at her answer key, she has 17.2486. Okay, and it has to do with, I think she probably only used 3 decimal places. Or I don't know, but, so,
Maybe she likes to truncate.
here's the deal. If you have something that is approximate to 17.25, guess what?
You're right.
You're good. So when you said 17.251, that's not wrong.
Yeah.
It all probably has to do with how you rounded, how you typed it in the calculator. So,
I think I'm fine with just one.
you think what?
6.
I think I'm fine with just 1 mile.
Okay. Questions on this one? Where am I at on time? Okay.
This is a long one.
It is. It is.
Oh, it's over here.
Okay. Moving along.
It looks pretty good yesterday.
I think it looks great.
And I will say, I may or may not have started laughing out loud when I was working on the homework.
LOL.
And we have a word problem about miles.
Oh boy.
It's not spelled right, but it just made me laugh.
How to spell it.
Is there a Y?
There is a Y in it.
Yeah.
But
Oh, I see it, number 10.
the fact that Miles, over spring break, our calculus class went to Candy Space Center, and I noticed Miles wore a rubberized suit, and he was acting a little sketchy as he left his group. Somehow Miles found a way to the roof of the 526-foot tall building to test out the bounce factor.
Nice.
And then it
Might I
has,
just say I was laughing to myself as I read this problem.
I can see that.
and then it has follow-up questions.
Yeah.
Maybe that's what
And
Miles is
number 10, Miles wasn't even bruised thanks to his suit.
In fact, he struck the ground and rebounded straight back up in the air at a velocity of 84 feet per second.
So that means
Okay.
that you're even going faster than that.
Right.
So it's a funny problem to begin with, and then the fact that we have a Miles in class just makes it that much funnier. Maybe it was just me that it struck as funny, but it definitely struck me as funny. So, okay. Example 3. Let's see if we can get this one in. Some motion problems will require you to find the actual position of an object or particle at a given point in time. Remember that you'll need to use initial conditions in order to find an actual position, since the definite integral only provides the change in position. It's only going to talk about how it changed from point A to point B. Example 3. An object moves in a straight line with the given velocity. At t equals 5, the object's distance from the starting point was 12 meters in the positive direction. write an integral expression that will compute the object's position at t equals 10 seconds. Thoughts? Notice we're not finding this value, we're just finding the expression.
I'm going to say 12 plus with the integral of 5 to 10, and then it'd be that for the dt.
Okay. Our initial position was 12 in the positive direction, right? So we've already moved 12 meters. And then we've got to look at the change in the position, right? So the change in position is going to be the integral from the beginning point 5 in a total of 10 seconds. So at 5, we had that point of 12, and then from 5 to 10. And you could write this as the integral from 5 to 10 of v of t dt. That's fine. Because v of t dt, if you use v of t in this problem, what's your grader going to assume you mean? This right here, because this is defined, yes? As long as that is officially defined, you can use v of t. Or the other way to write this is you could say 12 plus the integral from 5 to 10, the square root of 3t minus 2 dt. Those are equally correct, provided that v of t is defined to be that function. Okay? And that's all you do on that one. It was just our initial plus the displacement, if you will. Okay, B. Use a graphing utility to find the actual position of the object at 10 seconds. That is your calculator. And what are you doing? Plug and chug? Are we plugging in what we wrote last time? Yeah, and you can just plug that in exactly as is. You can just plug in 12 plus the integral from 5 to 10, the square root of 3t minus 2 dt. And what do you get?
34.5.
Oh no.
I have written down 34.5089. If we have a label, that would be meters. Okay. Now, if I go just 3 decimal places, it's what? 34.509 or 34.508, 34.5089, all equivalent on AP. Okay? They're going to look at your first 3 decimal places, and you can either truncate or round. Okay? Okay, do we have time for the next one? We can at least talk about it a little bit. Depends. I guess it depends if we do it by hand or on the calculator, whether we have time for it. How's that?
There's no calculator.
There is no calculator symbol, which doesn't always mean anything, but okay. A particle is moving along the x-axis with given velocity, measured in meters per second after t seconds, with an initial position. So we are provided a velocity and an initial position. Determine the displacement of the particle on the time interval 1 to 7. What are we doing here?
Same thing. Well,
How are we going to do the interval, the displacement on the interval from 1 to 7? Tell me the math I'm doing here. How do we do displacement? Displacement is an integral, yes. And displacement is just change in position from the beginning to change in position from the end, right? So this is just the integral from 1 to 7 of velocity. So integral from 1 to 7 of negative t squared plus 7t minus 10. It's just displacement. It's just on the interval from 1 to 7. So the initial condition isn't going to mean anything. Now, I have this one worked out by hand, probably because there was no calculator symbol. And, we're kind of at a situation where, okay, we're closing in on the end of the year. Do you know how to do this by hand? Do you remember how to do this by hand? Are you confident there? Because I'm not against us doing something like this on the calculator. I mean, there's pros and cons, right? On the flip side, do we also need to review this sometimes? Yeah. So, try and find a happy medium. Practice on the calculator, practice on the paper, I'll write down the integral, but I'm not going to have time to find it. Integral of negative t squared plus the integral of 7t minus the integral of 10, all evaluated from 1 to 7. So, did we get that? Negative 1/3 t cubed plus 7/2 t squared minus 10t. I'm going to say you can evaluate it by hand, you can use the calculator, and we'll start off with that answer tomorrow. Sound good?
Yay!
And then we'll still have to talk B. But B is going to take me a moment to talk about, so.